All right, so thanks everyone for coming to my master's seminar, where I will be talking about my thesis titled Dynamic-Occlusion-Aware Risk Identification for Autonomous Vehicles Using Hypergames. My name is Maximilian Kahn. Let's begin. All right, so the first point I want to make, and which is a key idea in this work, is that driving is a multi-agent problem. So what do I mean by that? Well, driving is fundamentally an interactive task where drivers reason over their best course of action, not in isolation, but in the presence of other drivers, and so have to consider how their actions will affect others and how the actions of others could affect them. A great example of this is of the white and black vehicle right here, which I'll highlight. So this, this black vehicle and this white vehicle. I'll just play forward a little bit here. You can see here the black vehicle doesn't just consider its optimal maneuver in isolation, but actually in the presence of this white car. And you can see here that this is an important idea because this white car is actually making a left turn, even though it's not in a left turn lane. It actually should be proceeding straight through the intersection here. And so the black car correctly anticipates this white car's maneuver and plans its optimal maneuver in the presence of this white car. In this case, which is to wait, as you can see. So we want autonomous vehicles to behave in a similar way to this black car. In other words, we want autonomous vehicles to take a multi-agent view when they plan their maneuvers. Luckily, this already exists, and it's called a strategic planner. So a strategic planner considers the autonomous vehicle's optimal maneuver by taking into account the maneuvers available to surrounding vehicles. Specifically, a strategic planner treats driving as a game theoretic problem where the players are vehicles on the road, and the goal is to maximize your utility in the presence of other vehicles who are also maximizing their own utility. Okay, so this is a minimal traffic game example to illustrate how a strategic planner works. So in this minimal example, let's consider the black vehicle from the previous video and a white vehicle. And in this example, let's consider the black vehicle to be an autonomous vehicle that uses a strategic planner. So in this situation, both vehicles have two available actions. They can either turn or they can wait. If they both turn, they end up with the lowest possible utility, reflecting that the outcome of these maneuvers is an unsafe situation. Now, a Nash equilibrium is a standard solution concept in game theory where no agent can increase their own utility by unilaterally changing their strategy. The two Nash equilibria are circled in red here. So one of the Nash equilibriums over here has the black vehicle turning and the white vehicle waiting, whereas this Nash equilibrium has the black vehicle waiting and the white vehicle turning. So how does the strategic planner decide which maneuver to make here for the black vehicle? So in our work, we select the utilitarian social welfare maximizing Nash equilibrium, which is just a fancy way of saying we take the Nash equilibrium with the largest combined utility value across all agents. So in this case, that would be this Nash equilibrium. And so the black vehicle decides to wait and predicts that the white vehicle will turn, which is exactly what happens in the video that we just observed. So I want to ask you this question now. What is the ultimate goal of autonomous vehicle research? Now, I would argue that it is to get autonomous vehicles onto public roads with people using them, right? However, for this to happen, they need to be safer than human drivers. And this is not really the case at the moment. Furthermore, amidst numerous autonomous vehicle-related collisions that have been circulated on the news, for example, people's trust in this technology is not particularly high either. So therefore, one of the most important next steps for autonomous vehicle development is proper safety evaluation. As a part of that goal, our work focuses on safety evaluation for strategic planners. In particular, we focus on the challenging subproblem of performing dynamic-occlusion-aware safety evaluation for strategic planners at intersections. To the best of our knowledge, this is the first work in this area. Okay, so why intersections in particular? So the idea here is that dynamic occlusion, in other words, occlusion caused by moving objects, such as vehicles, is a particular problem at intersections since there's ample opportunity for vehicles to block each other's view. And since vehicles are often moving along paths that intersect, there's also ample opportunity for head-on collisions. And this is an example of where occlusion caused by a moving vehicle results in a collision. So we have this oncoming vehicle that's going to enter this intersection here. We then have this left turning truck. And if I just place a little bit forward, you see that this truck is actually occluding this oncoming vehicle from this left turning vehicle here. And as a result, this vehicle actually decides to follow the truck into the intersection, and this results in a collision. All right, this is another example of where occlusion caused by a moving object results in a collision. So we have this emergency vehicle here, occluding the left turning vehicle on the opposite side of the intersection. And so there's gonna be an oncoming vehicle that comes through here. It can't see the left turning vehicle for a second or two, and it results in this collision here. A key difference between this collision and the other one is that here, the straight through vehicle here wasn't actually following the occluding vehicle. So there's a slight difference there. Anyways, so the point here is that dynamic occlusion is a real challenge, especially at intersections. And so that is why we focus on intersections in this work. Okay, let's now go over the thesis contributions, and this will also serve as an overview for the rest of the seminar. To start, let's address part A, which is on how we generate occlusion situations. So the motivation here is that there are a potentially infinite number of ways in which dynamic occlusion can occur. And so testing on only recorded traffic data cannot provide total coverage of all the occlusion situations that can arise while driving. In order to get around this, we augment naturalistic data with synthetic occluding vehicles in order to generate a much wider range of occlusion situations to test strategic planners on. In part B, we outline an occlusion-aware safety evaluation method for strategic planners using hypergames, which we believe is the first time hypergame theory has been used to model occlusion in autonomous vehicle research. We also use a novel dynamic occlusion risk measure, which helps us determine to what extent dynamic occlusion contributes to driving risk. And let's start with that first contribution. So how we generate occlusion situations. So this is an overview of how we generate occlusion situations. Starting from the top, we extract a full scene from a naturalistic traffic data set every single second. So each full scene is simply all the vehicles present at that particular time within the data. We then split each full scene into groups of vehicles, which we call partial scenes. The motivation here is that not all vehicles in the full scene are relevant to each other, and so we want to group them based on relevancy, as this will make simulation much less computationally expensive. Once we have the partial scenes, we then inject occluding vehicles to create occlusion situations. Now, depending on how the vehicles are positioned in the partial scene, we can end up with different numbers of occlusion situations. So that's why in this case, we can end up with 3 occlusion situations for this partial scene. This one only leads to 1, so on and so forth. Okay, so this is all fairly abstract. Let's make things more clear with a running example. Okay, I think the most intuitive way to explain how we generate occlusion situations is to show you an example of one at the start. So this is an occlusion situation we generated using our method. The whole idea behind the occlusion situation is to create potentially dangerous occlusion situations for the subject vehicle. So here we have the subject vehicle over here. We have 2 relevant vehicles, and we have the occluding vehicle. The relevant vehicles are included because they are relevant to the subject vehicle's behavior. So they will actually determine what the subject vehicle will do. The occluding vehicle is here because it occludes one of the relevant vehicles from the, one or more of the relevant vehicles from the subject vehicle. So in this case, for example, relevant 2 is occluded from the subject vehicle. So this is the end result. Let's now cover the steps to get here. Okay, so this is an example of a full scene from the Waterloo multi-agent dataset, which is the dataset we used in this work. This footage, for those who are curious, was actually taken at the University and Weber intersection in Waterloo, Canada. So our first step is to decompose the full scene into partial scenes, which means we need to identify which vehicles are valid subject vehicles. Since we are focusing on creating dangerous occlusion situations for testing the subject vehicle, each subject vehicle must have a green or yellow light. Exceptions are made for right turning vehicles, since you can make a right on a red in Ontario. The circled vehicles are valid subject vehicles because if a vehicle is occluded from them, that could lead to a risky occlusion situation. We don't consider any of these vehicles any of these non-circled vehicles to be subject vehicles because they have a red light. And so even if a vehicle was occluded from them, there is no danger because they cannot move. So each of these subject vehicles will get their own partial scene. And to give an example, let's look at the partial scene for this subject vehicle in particular, which will form our running example. So it's the subject vehicle, and there are two relevant vehicles in this partial scene. In order to be a relevant vehicle, the subject vehicle, so in order to be a relevant vehicle to the subject vehicle, the vehicle must be either leading the subject vehicle or in a conflicting path to the subject vehicle. And you can see here actually relevant vehicle 2 satisfies that second requirement because the subject vehicle here is going to be making a left turn. So this is its path, whereas relevant vehicle 2 is going to be proceeding straight through the intersection. So there will be a conflict somewhere here. So therefore relevant vehicle 2 is in a conflicting path. We include relevant vehicle 3 because it is leading relevant vehicle 2 and thus can affect the behavior of relevant vehicle 2, since relevant vehicle 2 may decide to match vehicle 3's speed and maintain some kind of minimum distance gap with relevant vehicle 3. So this is the partial scene. This is an example of the partial scene. Now let's see how we inject occluding vehicles. Okay, so the next step, once we have the partial scene, is to inject an occluding vehicle. We could use random sampling to spawn occluding vehicles, but that would be inefficient, since we might end up spawning vehicles on the sidewalk or in other unrealistic areas. Instead, we leverage the intersection map to spawn occluding vehicles along the center line of each lane, spaced roughly 1 meter apart. This gives us adequate coverage over the entire intersection, while also making sure the occluding vehicles are spawned in realistic locations. So you can see here the red dots show all the locations where we try spawning occluding vehicles for each partial scene. This is the criteria we use to check if a synthetic occluding vehicle, which I'm now going to refer to as SOV, if an SOV spawn location is valid or not. So first we check if the SOV's bounding box is a minimum of 1 meter away from all other vehicles. Then we check if the SOV is in a lane with the green or yellow light. The reason being that we don't want an SOV with a red light to be spawned in the middle of the intersection, since that would make no sense. Next, we check that the SOV is within the subject vehicle's field of view, which is modeled by the green and the blue regions. So the size of each region represents how much attention the subject vehicle here too, pays to each of the other vehicles. The idea being that the subject vehicle pays more attention to vehicles that are closer because closer vehicles are more relevant to the subject vehicle's behavior. This is why in the first image, the green region is much larger than the blue region, since this vehicle is much closer to the subject vehicle. Whereas in this second image, we see that these two vehicles are roughly the same distance from the subject vehicle, and therefore their FOV regions. In other words, the amount of attention the subject vehicle allocates to both vehicles is roughly the same. So in our running example, so over here, there's only one valid SOV spawn location. But I want to give, for contrast, another example scene where there actually are multiple valid SOV spawn locations. And so this is what I meant when I said that the configuration of vehicles in the partial scene determines how many occlusion situations can be created, right? So here we can only create one, here we can potentially create many. This next is a comparison for a running example between the partial scene where there is no occluding vehicle and the occlusion situation where we've now incorporated the occluding vehicle. And we're looking at this from the perspective of the subject vehicle's vision. So we use a grid-based raycasting approach to model the subject vehicle's vision. The red lines represent areas where the subject vehicle can see, and the gray regions represent areas that are occluded from the subject vehicle. So in the partial scene, we see that both relevant vehicle 3 and relevant vehicle 2 are visible, whereas we see in the occlusion situation with the occluding vehicle here, now relevant vehicle 2 is occluded. So this is how our method automatically generated this occlusion situation from naturalistic data. I just want to briefly mention, coincidentally, this situation almost exactly resembles the real-world occlusion situation I showed at the start. The blue circled occluding vehicle you see in the video is essentially in the same position as the occluding vehicle that we automatically generated. This left turning follower vehicle is in roughly the same position as the subject vehicle, and the oncoming vehicle from the other side of the intersection is in roughly the same position as relevant vehicle 2. Okay, so that concludes the short overview of how we generate occlusion situations. Now I want to go over how we perform occlusion-aware safety evaluation for strategic planners. So the first question to answer is, how do strategic planners in our implementation work? Each strategic planner instantiates a hierarchical traffic game. On screen, you can see an example of this between two agents. So we have agent 1 here and agent 2 up here. So agent 1 has 2 available maneuvers. It can either wait for the oncoming vehicle to pass, which is represented by this blue trajectory here, this arrow. It can also proceed with its left turn, and that's represented by its red trajectory here. Agent 2 can either decelerate to stop, which is this blue trajectory, and that's this maneuver here, or it can proceed at track speed through the intersection, which is represented by this red trajectory here. So this game is hierarchical because it is split into 2 levels. So at the top, we have the agents play the high-level maneuver game, which determines which maneuver they will choose to take, and then they play the low-level trajectory game to determine what trajectory to use for that maneuver. We can actually use something called backward induction to solve this game. The motivation being that we don't actually know the utility values for the maneuvers at the start. So what we do is we first solve the trajectory level game, meaning that we select a representative trajectory for each maneuver first. Once we have assigned trajectories to each maneuver, we can compute the utility of each maneuver, which is a combination of how safe the trajectory is and how much progress the trajectory makes toward the vehicle's intended location. Once we have utilities for each maneuver, we can then solve the maneuver level game by solving for the Nash equilibria. More formally, a hierarchical game is defined as the following tuple, where n is the number of agents in the game, m is the set of driving maneuvers available to each agent in the game, t is the set of trajectories representing each maneuver, and u is the utility function, which maps trajectories to utility values in Rn. However, there is a big problem. Standard game theory has difficulty modeling occlusion since games are instantiated with the implicit assumption that each agent is aware of every other agent participating in the game. So in order to incorporate occlusion into game theoretic traffic models, we propose the novel use of hypergames. So hypergames allow us to incorporate misperceptions into standard game theoretic models. Specifically, a misperception can be either 1, having an incorrect understanding of the preferences of other agents, 2, having an incorrect understanding of the actions available to other agents, or 3, and most importantly for our work, not having awareness of all other agents playing the game. I mean, that's essentially what occlusion is, right? Or 4, any combination of the above. We also use the hypergame hierarchy of perspectives proposed by Wang et al., which splits hypergames into multiple levels of perspectives. So we call the level 0 hypergame the occlusion resolved perspective. So here we don't actually incorporate occlusion into the game, and so each agent in the level 0 hypergame can see every other agent. In other words, the level 0 hypergame is simply the single game G. In contrast, the level 1 hypergame, which we call the occlusion naive perspective, we incorporate occlusion. But agents are not aware that occlusion is present. So every agent constructs the game from their perspective. So for example, G sub 1 is the traffic game from vehicle 1's perspective, and only vehicles that are visible to vehicle 1 are included in vehicle 1's game. And this applies to all other vehicles as well. The level 2 hypergame uses what we call an occlusion-aware perspective. So here, what it means is that each agent is aware that occlusion is actually present. And so here each agent constructs a level 1 hypergame, modeling what they believe to be the games that each agent is playing. Technically, this hierarchy can go to a finite level L. For our work, though, we only need these first 3 levels. So let's look at how we use hypergames by using this running example that we generated in the previous section. So if you recall, we have the subject vehicle here, otherwise known as agent 1. We have agent 3, the SOV, and agent 2. Okay, so this is this is the level 0 hypergame for our running example, where each agent can see every other agent. So note that we model each agent's behavior using a strategic planner here. So agent 1 has 2 available maneuvers. It can either follow the SOV into the intersection, or it can wait. The SOV can either proceed with its left turn, or it can wait. Agent 3 only makes sense for it to have one maneuver, since it's already exiting the intersection. So its only maneuver is to exit the intersection at track speed. And agent 2 can either proceed at track speed, or it can follow agent 3. The difference between these two maneuvers is that executing a track speed maneuver means to try to hit the speed limit, whereas a follow maneuver means to try to maintain the same speed as the leader. At the bottom here, you see the utilities for each of these strategies. Okay, this is the level 1 hypergame. It's a little different. So here we incorporate occlusion. So from agent 1's perspective, only agent 3 and the SOV are included in its traffic game, you can see here, because agent 2 is occluded. Likewise, agent 1 is not included in agent 2's game because agent 1 is occluded from agent 2. This is the game from agent 3 and the SOV's perspective, and you can see all 4 agents are included because all 4 agents are visible to the SOV and agent 3. So that is what the level 0 and the level 1 hypergames look like for this running example. The next question to answer is how we evaluate these strategic planners using these hypergames. And for that, we're going to use the dynamic occlusion risk measure. So here, T sub H naught is the set of trajectories each vehicle uses in the level 0 hypergame. T sub H1 is the set of trajectories each vehicle uses in the level 1 hypergame. And S is a surrogate safety metric, just measuring the overall safety of the situation. In our case, we use the minimum distance gap. So what is this measure actually saying? Well, this first term is essentially asking the question, what is the minimum distance gap if we were to simulate the level 0 hypergame? Whereas the second term is asking the question, what is the minimum distance gap between all vehicles if we were to simulate the level 1 hypergame where occlusion is present? Now, if this first term is much larger than the second term, that would imply that occlusion plays a large role in contributing to driving risk, because the only difference between these two terms is that we incorporate occlusion into this second term. We also define an OCC, in other words, an occlusion-caused collision, when there's no collision in the level 0 hypergame simulation, but there is a collision in the level 1 hypergame simulation. So in other words, implying that occlusion was the cause of the collision. So with that out of the way, let's now see if our running example is a high-risk occlusion situation, shall we? So this is the level 0 hypergame again for our running example. Here there are 2 Nash equilibria. And if you recall, the strategic planners determine the maneuvers to execute based on the Nash equilibrium with the highest combined utility value. Now, in this case, actually, both Nash equilibria have the same combined utility value. So we just randomly select one. I'm going to randomly select the first one. So here, agent 1 waits. The SOV proceeds with its turn. Agent 3 proceeds at track speed, and agent 2 proceeds at track speed. In this simulation, there is actually no collision. Here, the SOV manages to make its left turn before agent 2 gets too close. And because agent 1 is waiting, there's no collision between agent 2 and agent 1. And the agent 3 just exits the intersection. Now, this is not quite the case in the level 1 hypergame. So over here, we see that agent 1 actually decides, so from agent 1's perspective, this is its traffic game, right? This is what it uses to determine its maneuver. You can see that is a different kind of Nash equilibrium here. And its selected maneuver is actually to follow the SOV. And this is a key difference between the level 0 and the level 1 hypergame. And this is only because the agent 1 does not include agent 2 in its traffic game. But as a result, the level 1 hypergame does actually result in a collision. So this is what the level 1 hypergame simulation looks like. So you have agent 2 coming through the intersection with the SOV proceeding with its turn. And let me just start this a little bit here. And you can see there's a collision between agent 2 and agent 1 because agent 1 actually follows behind the SOV, and that results in that head-on collision. Okay, So I think I'm running out of time. So I just want to highlight two quick results from the thesis, the two kind of most important results, I think, from the thesis. At the start, I said that recorded traffic data cannot provide total coverage of all the occlusion situations that can arise while driving. And indeed, we were only able to find 2 occlusion-caused collision examples in the naturalistic data, right over here. Which is not a reflection that the strategic planners we used were safe, but rather a sign that we didn't have enough occlusion situations to really get a sense for how strategic planners perform under occlusion. However, when we injected SOVs into the naturalistic data, we were able to increase the number of occlusion situations from roughly 1,500 to approximately 106,000. This allowed us to find 77 more unique occlusion-caused collisions, highlighting where the strategic planners, where they failed. A major benefit of having more results to draw from was that it allowed for a much richer analysis of the nature of how occlusion situations form. In fact, using our results from our occlusion situation generation, we were able to construct a taxonomy of occlusion situations by observing our results. And I want to share that taxonomy with you now. So these are the unique high-risk occlusion configurations that ended up leading to occlusion-caused collisions. These circled vehicles in red are the colliding vehicles. The circled vehicles in blue are the occluding vehicles. At the top of the taxonomy, we split occlusion situations into either left turn across path, in other words, LTAP situations, and right turn, in other words, RT situations. So LTAP situations occur when one of the colliding vehicles is making a left turn and the other colliding vehicle is proceeding straight through the intersection, whereas an RT situation occurs when one of the colliding vehicles is making a right and the other is proceeding straight through the intersection. Out of the 79 occlusion-caused collisions we were able to generate, 77 were LTAP situations and only 2 were RT situations, which is kind of interesting. So we next split occlusion situations based off if they are tag-on or reveal situations. So tag-on simply means that one or both of the colliding vehicles was tagging on behind the occluding vehicle. So for example, we have left turn tag-on situations where one of the colliding vehicles is tagging on behind the occluding vehicle. We have straight through tag-on where the straight through vehicle is tagging on behind the occluding vehicle. And we also have both tag-on where both the left turn vehicle and the straight through vehicle are both tagging on. Now, if you're curious what kind of collision happens here, this typically, what we observed actually results in sideswipe collisions. And what ends up happening is that these two vehicles, because they're occluded from each other, they actually end up driving too close to the center line. And so they end up in a, in a sideswipe collision situation. We also have reveal situations, which occur when neither colliding vehicle is in the same lane as the SOV. So you can see that over here and over here and over here, for example. Now, while one in theory could come up with this taxonomy analytically, we managed to generate each of these occlusion situations using our method. And so the taxonomy actually naturally emerged from our results. Okay, so that's where I want to wrap it up today. So in conclusion, strategic planners can be a powerful tool to perform behavior planning in a multi-agent environment. However, in order to make this technology publicly available, these systems need to undergo proper safety evaluation. So we contribute to this research effort by 1, proposing a method to significantly increase the number of occlusion situations in naturalistic data for testing, and 2, outlining how hypergames can be used to test strategic planners in dynamic occlusion situations. Our hope is that this work can be used as a stepping stone for future research into occlusion-aware strategic planner safety evaluation. Before I end, I just want to briefly give some acknowledgements here. You know, a master's thesis is a large undertaking. I can confidently say I would not be here today were it not for the amazing people who helped me along the way. So first, I'd like to thank Patricia Sarkar for her support with this thesis, which in large part is built on top of her own work on game theoretic traffic models. I'd also like to thank my supervisor, Dr. Krzysztof Czarnecki, for his insightful advice and feedback throughout this work. I'd also like to thank Dr. Kate Larson and Dr. Saeed Zahidi for agreeing to be my thesis readers. And finally, I'd like to thank all the amazing WiseLab folk whom I've had the pleasure of working with these past couple of years. So that's it, and thank you all very much.